Hi everyone, this is Danny. This is the second lecture, or the second series of slides and commentary from me for your Anthropology 1 Introduction to Biological Anthropology class. So, in the previous lecture, I said briefly that one of the things that distinguishes biological anthropology from other kinds of anthropology is that biological anthropology is a scientific pursuit. And that its practitioners consider themselves to be scientists and work within an explicitly scientific frame of reference. So this lecture is going to be about what is science, and you might think that this will be the most boring lecture. I think it's one of the more important lectures that I can offer you because I want you to think about science itself from an anthropological perspective. That is, I want you to think about science as something that humans do in groups and something that has a real material product. In our case, knowledge and the technology that we derive from the knowledge that we get through scientific research. Well, here, let me explain it. By the way, I don't hate science. The Natalie D comic is just a joke. Lots of jokes in this lecture, you'll see. All right. So you are probably already familiar with something called the scientific method. This is what they teach you science is like in grade school. It's not really completely accurate. It's way overly simplified. But the scientific method supposedly starts off with somebody asking a question, then doing some background research about that question to see what other questioners have asked and answered. And then they formulate something called a hypothesis, which is a kind of statement that can be tested. Then they go about testing that hypothesis. In grade school science classes, they often teach that scientific testing is done through the model of experimentation, that is, setting up an experiment and running it. But that's only one way of doing science. We'll talk about that again later when I get to talking about natural history, but there are other means of doing science, including observation, comparative analyses, or specimen collecting, all sorts of ways to do science. It's not all about experiments. But then in the scientific method, as it's taught in grade schools, there's a fifth step where after you have completed the testing of your hypothesis, you evaluate the data or the outcomes of your experiment or your observations. And then the last step, you draw some conclusions. You try to make a statement about the world based on the data that you have collected. Well, as I said, that is a simplistic model of scientific research. I do not want you to remember this. Don't bother writing down these 6 steps. I'm sorry if you already have. What science really is like is this. Well, again, this is probably only slightly more accurate than the 6 steps to the scientific method that I outlined on the previous slide. But this model here really does seem to get to the complexity of the forces shaping the production of scientific knowledge. Right? Science is not a easy kit that you get in a box and you put together, and then at the end of your little foray into science, you have a fact. You don't just follow the scientific method and end up with a handful of facts. No, no. Science can start with all sorts of inspirations, curiosity, new technologies, practical problems, serendipity, meaning maybe you just bump into a problem or something interesting, a surprising observation, or a personal motivation. Maybe you're very motivated to cure a particular disease. These motivations, these human motivations, feed into a phase represented in the red circle at the top of exploration and discovery. Where you're exploring the literature, you're reading what other scientists and scholars have learned in the past, what they've figured out. You're sharing your questions and your findings. You're asking questions. This stage, the exploration and discovery stage, can parlay into a point where you're gathering data. You're making hypotheses. You are making observations, maybe testing them through experimentation. You interpret that data. And gathering and interpreting data, again, these are linked processes. There is always a level of interpretation to data. If anybody ever tells you to can your critique, let's just stick to what the data tells us. What they are actually doing is making a claim to their own interpretation of the data. Anytime somebody says, well, let's just affect that XYZ, they are making a claim about their interpretation of some data. And while that doesn't mean that you can just dismiss people, because we all are involved in interpretation, I do want you to think about that. Think about the fact that there is no just flat out data out there for you to grab and use as if it was a particle that existed in a vacuum. Rather, data is always cloaked in human interpretation. There is no data for us without us also interpreting it. Anyway, you get through this data phase, this phase of testing ideas. And this can then parlay back into exploration and discovery, or it can go into the community for analysis and feedback, or it could go into I guess, an implementation phase, here labeled as the benefits and outcomes portion, where you would build knowledge, inform policy, develop new technology, address a problem out there. And then, of course, these things all move around together. So scientific research, the production of scientific knowledge, is not an easy 6 steps. It's actually quite a complicated process, and it's being inflected upon and affected by a multitude of forces in society and in our personal lives all the time. It's a human process doing science. So with this difficulty of talking about what science is, well, right, there's a difficulty in talking about what science is. My personal crutch that I prefer to use is 4 aspects of science outlined by the biologist Ernst Mayr. I think he outlined these in 1997. It'll be on the next slide or the one after that. But so Ernst Mayr was a biologist. He was involved in some important debates within the academy about the role of scientific knowledge vis-a-vis the knowledge produced by non-scientists, such as people working in the humanities or people working in the social sciences. So he had 4 aspects of science that he thought distinguished science from all other intellectual pursuits. The first one is community. And for community, in order to grasp the importance of understanding science as a community process, I want to introduce you to 2 kinds of characters that you are already probably familiar with. The first is the genius. We have here at the bottom of this slide 4 images of people who in our society are often considered to be geniuses. I've got Stephen Hawking on the right, the great British physicist. I've got Albert Einstein there beside him, the German-American physicist again. Then next to the left of Einstein is Charles Darwin, the British natural historian. And then one of my favorites, all the way here on the left, is Carl Sagan, the astrophysicist or astronomer who hosted and wrote the original Cosmos series. Cosmos is now in reboot, as they say nowadays, with Neil deGrasse Tyson taking over Carl Sagan's role. You should really see the 1980s Cosmos. It's really, really good stuff. I haven't seen the new one yet. Anyway, that's a bit of a tangent. We'll talk about Neil deGrasse Tyson in a little bit. These folks are considered geniuses by our society. Well, I don't want you to get carried away with this genius thing. Okay, look, I'm not going to say that there aren't people out there who have developed intellectual skills that exceed the intellectual skills of others. By that, I only mean that, for instance, somebody like Charles Darwin worked very hard at understanding the natural world. He worked very hard at writing. And he honed these skills to the point where he came up with a pretty good idea. But then again, he did not come up with that idea on his own. You may have heard of a gentleman named Lord Alfred Russel Wallace, who we will talk about in a couple of lectures, who also contributed a lot to Darwin's notion of evolution through natural selection. And then before them and contemporary with them also were uh, entire cadres of scientists working on the problem of evolution. Lots of people were thinking about evolution when Charles Darwin was doing his research. He was merely one voice to rise up out of a crowd and get notice. And he had the right connections, the right position, the right voice, and the right idea for his voice to get picked up and to become this sort of ideal genius voice in our society. Um, Basically, what I'm saying is he was a smart guy, right? A hard worker. All these guys, smart guys, hard workers, uh, but they are also, in a very important sense, just the guys who happen to get published, happen to get on television, happen to be in the right place to make the right impact. What distinguishes a genius from somebody who doesn't get to consider themselves a genius is only two things. First thing is job skills. Second thing is having a job that people will tend to ascribe intelligence to. I mean, your professors, scientists, these are people who, as a very particular job benefit they enjoy, get to be considered highly intelligent people. Let me tell you, not to say your professors aren't intelligent, but they've just got job skills. Intelligence is not something that we can measure in one way. And anyway, it's not ever going to be a singular genius who comes up with the big idea. It's not ever going to be, well, I mean, sure, maybe sometimes, who's going to rule it out? But most of the time, what you see as a genius is really one person who's kind of emerged as a face from a mass of people doing important work. I want to impress that upon you. Science is a community effort. Another kind of character that will help you understand why it's important to understand science as a community effort is the mad scientist who does mad science. My current favorite mad scientist is the one played by Albert Decker in the 1940 movie Dr. Cyclops, which I just saw the other night on Svengoolie on MeTV. He's always showing these awesome old horror movies from, Universal Studios and other studios of the 40s, 50s, 60s, 70s, whatever. Anyway, a mad scientist is a guy. He's sort of the monstrous version of a genius, right? Oh, everybody loves Albert Einstein. We all want to give him a hug. Even Darwin is sort of huggable. Carl Sagan, very huggable. I was going to say Richard Dawkins, but rather Hawking here, Stephen Hawking. He's he's a little bit of a curmudgeon. He doesn't try to make himself lovable, but people do anyway. It's funny. So the monstrous version of a genius is the mad scientist. He's the guy who thinks he's got access to the truth. He's the guy who knows he's the genius, and he doesn't need your help. In fact, he's convinced you don't understand him and that the scientific community, when it poo-poos his ideas, it's just wrong. So what does the mad scientist do? He goes off into the jungle and builds a compound. Or he climbs into the Carpathian Mountains and builds a castle and starts reanimating dead bodies. Dr. Cyclops here. Yeah, they called him Dr. Cyclops once or twice in the movie. It wasn't the character's actual name. But anyway, Dr. Cyclops here, his mania happens to be for shrinking people. Right? He's convinced he's got the answer to some of humanity's biggest problems and that his research is very important. But really, he's just all by himself in the jungle. That's not where important information comes from. I'm not saying, the real jungle doesn't have some lessons for us. But this kind of intellectual jungle that the mad scientist secludes himself in, it's one that's removed from community, it's removed from society, and therefore it can't really produce ideas that are, A, useful to us, B, comprehensible by the rest of us, including the scientists, or C, relevant. Shrinking people, Dr. Cyclops, really? What are you going to accomplish by doing that? So, what being in a community affords us are three very distinct advantages. Number one advantage, no one can be in command of all knowledge, not even all knowledge on one topic. That should be pretty self-explanatory, right? We're all specialists. Second, working together keeps individuals from having to learn everything for themselves. My goodness, wouldn't it be so crazy if physicists had to figure out the basics of classical physics all the way back from the time of Isaac Newton all by themselves? Just so that maybe, very, very late in life, in their 80s or 90s or hundreds, they could start making progress in contemporary physics, quantum physics, which are built upon the foundations of older kinds of physics. So working in a community means that we don't have to restart and reinvent the wheel every time we want to do research. There is research already done out there by the multitude of scientists who never get recognized as geniuses. Third is working together allows for greater specialization, which allows us to push our limits more effectively, right? If Albert Einstein had to become a generalist and understand chemistry and biology as well as his physics, for instance, then would he have been able to push and make that breakthrough that we now call the theory of relativity? I don't know. Rather than geniuses and mad scientists, I want you to think of scientists as blind sages. I really like this parable. You find different versions of it in Buddhist tales and in Hindu tales. All the different versions, focus around this set of characters, these blind sages. There's 8 of them, or 10 of them, or 12 of them, or 14 of them. I don't know. Different numbers and different stories. But these blind sages, they keep together as a group so they can take care of each other. And they're going down the road one day, and they encounter this object. They don't know what the object is, so they move out to investigate it. They're blind, so they can't see it. What do? They touch it. One guy says, "Ha! The thing is sharp and long. It must be like a sword." "No, the thing is long and muscular. I think it's like a python." "No, it's tall and stout. It's something like a tree." "No, it's very high, and it's very hard to get to the top of. I think it's like a mountain." "No, it's broad and firm. I think it's like a wall." "No, it's soft and it has tassels. It must be like a broom." What the sages won't realize, if they don't talk to each other about what they're experiencing, is that the object is an elephant. It's not a sword or a snake or a tree or a wall or a mountain or a broom. These experiences are just the individual experiences of the truth that the individual blind sage can have. Without his power of vision in this case, the sage can't step back and see the whole picture and see, oh, it's an elephant. Rather, the entire community of sages must move in on the elephant, describe the parts of it that they can grasp, and then relay that information to everybody else. I think the blind sages is a much more accurate way of thinking about the role of the scientific community. Scientists from different disciplines and with different personal aptitudes will find different things in the world. And it's only through the communication of these different ideas that they will be able to come up with a more accurate vision of what's going on. So in the West, well, actually, I always say this in the West, a peer review, I guess, was developed in the Western Academy, but it's really a global thing. It's all over the world. Everywhere you go, universities and corporate science is conducted through peer review. And peer review is a formal process of sharing scientific or scholarly reports with other experts in order to verify the findings. So peer review is when the blind sage who has the elephant's tusk cries out to the rest of the sages, "I have a thing that is long and sharp and hard. I think it is like a sword." And then he describes it in more depth. And what the other sages will do is they will vet that report against their own findings. And they will make a determination, sometimes flawed, but this is how we have to do it. They will make a determination about whether or not that report is important and accurate. So what peer review does is it allows us to consider the evidence and to consider the conclusions that scientists and scholars reach. And then only after a community has considered those conclusions and verified it can we act on that. That's why I have this little photograph of this protester holding up a sign. What do we want? Evidence-based change. When do we want it? After peer review. What this person is probably referring to is research on climate change. So many politicians in Washington say climate change is not scientifically proven. So many journalists will say climate change, well, there's a variety of ideas about it. There is a contingent of people who don't think it's happening. No, no, no. The scientific consensus is by and large that, yeah, humans, we're causing massive climate change all over the planet. Peer review has seen the articles, the reports, the publications that document this, and has found them to be important, verifiable, and empirical. We'll talk about what empirical is in just a second. Reports that claim that climate change is not happening, or it is not caused by humans, a very, very small number of these reports get through peer review. Is it because scientists are overwhelmingly liberal? No. It's because scientists are overwhelmingly scientists, and they don't want to have the authority that they have in society, and scientists do have authority in society. You know, somebody tells you they're a scientist, and you go, ooh, this person must know something. And scientists don't want that authority to be degraded. They are very careful with it. We as a community watch each other's backs through peer review, making sure that we're not out there in left field saying crazy things. So the second aspect of science identified by Ernst Mayr is much less complicated in my opinion here. It is the scientific attitude. And Ernst Mayr himself, he got to be very old. I think he died in 2001 or 2002. I think he was 101 years old. He very concisely put the scientific attitude as open to challenge. There is a reason for this, right? You have to be open to challenge. If you're not open to challenge, if you think that you've got the answer and you don't need anybody else's input or criticism, what does that make you? It makes you Dr. Cyclops. It makes you a mad scientist. Dr. Cyclops, Dr. Frankenstein, Faust was a mad scientist. So the knowledge that is produced by scientific research is provisional truth. Let's talk about that on the next slide. Provisional truth is really an aspect of the body of knowledge that science is. This is the third thing that Ernst Mayr identified science could be. It's a body of knowledge. It's the facts, it's the figures, it's the data, it's the knowledge, it's the things in the world, it's the science. It's the knowledge, it's the product of scientific research. Scientific research makes things, and it doesn't make technology. That's another step down the road. Scientific research makes knowledge, and it makes a particular kind of knowledge. And I identify this kind of knowledge as provisional truth, which is truth that can be updated as the evidence changes. I have a picture here of Wikipedia again, and I think Wikipedia is a great example of a community of learned individuals and a lot of yahoos working together to create provisional truth. And I mean Yahoo in the best way possible. I've contributed to Wikipedia, and I'm not a scientist. I am a learned individual about some things. Anyway, job skills. Like I said, job skills. But the reason I think Wikipedia is cool is because it's always getting updated. Sometimes the updates are graffiti, you know. Sometimes people go in there and they insert a crude word in the middle of an article, or they write articles that they know are not true, or they go to the web page, the Wikipedia page for the politician they work for, and they adjust that personal background a little bit. It really happens. But science itself, Wikipedia aside, science itself produces provisional truth, right? If you think you've got the answer, you're a mad scientist. If you think that the knowledge you're producing won't be changed or can't be changed or won't be made more accurate in the future, you're a mad scientist. If you think what you're doing is the only worthwhile scientific pursuit, you're a mad scientist. The truth that science produces is provisional. It's not going to be a statement about the universe that is absolute. It's going to be a provisional statement at best. Now, to get our heads around this question of the truth, I want you to be familiar with two terms: positivism and relativism. Positivism is a position that holds that there is truth in the universe, that there is some knowledge that can be absolutely known. This would be the idea that there are facts, that there are these individual nuggets of data out there that, no matter how you interpret them, are going to be true anywhere. We often think of math as producing positive truth. 1 plus 1 always equals 2. Well, math is actually not necessarily positive truth. In fact, quantum mechanics suggests that particles can be in two places or more than one place at once. So the 1 of 1 plus 1 equals 2 could actually represent a multitude of positions. So 1 plus 1 could easily equal 7, if you're following the implications of quantum physics. This would be a relativist point of view. And that is a position that holds that knowledge and truth are relative, i.e., that knowledge is only true under certain circumstances. Right? For quantum physics, the knowledge you derive from a particular set of observations is only true for that set of observations. For cultural anthropologists, the knowledge they talk about in the quote-unquote cultures, quote-unquote societies that they study is generally only true in the context of those cultures and societies. They don't try to generate knowledge about all humans everywhere. They try to generate knowledge that's going to be relatively true from the point of view of one particular situation in the world. So in practice, most people are a little bit of both. I find that, for instance, a scientist might, some scientists will, poo-poo religion. Say, oh, religion, yeah, they think they have the capital T truth, but, science actually does. So, positivism often becomes kind of an argument between different versions of positivism. That's the problem with positivism. That once you think that you've got the capital T truth, well, then you've still got to deal with all the other people who think they've got the capital T truth also. Relativism makes it easier to be nice to people who have other ideas about the universe. Well, that's one benefit. There's actually a lot more at stake in these two terms, but we'll talk about them more later. Oh, and then yes, I almost forgot. Velociraptor. No absolutes? Are you absolutely sure? Take that, relativist. The fourth and final aspect of science identified by Ernst Mayr is method. Science follows a very specific method. It's called empiricism. Science is empirical. Empiricism is any methodology that produces knowledge based on observable phenomena. The real benefit from producing knowledge empirically is that it allows us to recognize our limits. This isn't to say that I'm going to be a defeatist here and say that humans have limits about what they can know. What we can know is going to keep changing in the future as we change, as our technologies change, as our questions change, as our problems change. But what empiricism does is it reins us in. It keeps us locked up in the world of the material. Now, that might be a bad thing if you are, say, I don't know, somebody seeking transcendence, but that's not a scientific pursuit. We're talking about science here. Science is dealing with the material, with the world that is in front of us, the things you can knock on. right? That's what science deals with. Things you can knock on, things you can see, stimulus. But there is a problem with that, right? So I give you David Hume, an English philosopher of the 18th century. He formulated the contemporary notion of empiricism, or he laid the foundations for it, we could say. I think he coined the term empiricism, actually. He had an interesting parable. He had a lot of little thought experiments and parable-like stories. One of them is about the sun. How do you know that the sun is going to rise tomorrow? No, really, how do you know? Oh, some of you who get up in the morning may have noticed that the sun has risen every day of your life up to now. So you might extrapolate out from that into the future. But then what is the real concrete material connection between tomorrow and what we've observed in the past? There may not be actually any empirical material connection between these two areas of reality. Right? Well, I give you that parable as a way to think about an extreme version of empiricism, limiting us to only what we have seen. The future, in this case, would be completely outside of human knowledge. Well, that's not even extreme. I think that's just reasonable. I give you this other picture here of a dolphin because I want you to understand that even though empiricism grounds us in the world of the material, in the world of matter, that world is going to be a different world for everybody depending on their point of view. The dolphin is an extreme example. Dolphins sense their world through sonar. In order to sense its world, a dolphin makes a squeak inside its nasal sacs by forcing air through them. That squeaking vibration is then modulated in a muscular melon in its head, and then sent out into the water around it, where the sound vibrations will encounter fish and other objects, bounce off of them, return to the dolphin, vibrate its jawbone, stimulating the mandibular nerve connecting to their brain, where, in some sense, the dolphin then forms an image of its world from this sound data. The sensory equipment that a dolphin has to sense its world is drastically different from the sensory equipment that we have to make sense of our world. If you were down under the ocean, you would see a fish. But in a very real sense, your experience of that fish and the dolphin's experience of that fish are incommensurable. They cannot be compared to one another. They can be in some respects, but they're never going to be subsumed into the other. Right? The visual stimulus of the fish and the vibrational stimulus of the sonar wave bouncing off the fish are creating different worlds for the human and the dolphin. Less extreme examples are all around us. People see the world in different ways. They have very different approaches to problems. They have different analytics built into their heads for answering and asking questions. So even if we are rooted here in the material world, we're still going to be coming up with a lot of different kinds of knowledge. And then again, that gets us back to why community is important. Don't you think a dolphin and a human working together might get a better idea of what a fish is all about than if you were just looking at a fish or just sensing it as a vibrational object in the ocean? I think so. So, now that I've identified for you what science is, and I hope you wrote down those 4 aspects and have come to some sort of understanding of what I'm talking about with each of those. Now that I've identified for you what science is, I'm going to tell you a little something about the way I structure the class. In the first half of the class, I addressed the theory of evolution. That is, I addressed the history of ideas, I addressed the people who have talked about evolution, the people who contributed to our contemporary understanding of how evolution works. And then the second half of the class, I talk about the process, the real thing that happens in the world. And I focus mainly on the process of human evolution, where we come from. So what this gets me to is a need to talk about what a theory is, because this is the first half of class, and I'm going to be talking about evolutionary theory in the next, many lectures. So you should know what a theory is. This is a contentious word, too, when we talk about evolution in the public sphere. So let's get a fix on it. We often hear, evolution, that's just a theory. We mostly hear this from people speaking in a particularly politically charged climate in the United States, where for some reason people have decided to organize themselves into two groups, religious creationists and diehard evolutionists. And I don't really see the point in forming these little coalitions and hating each other so much. And I don't know, maybe I spend too much time on the internet, because right when you associate with people, they never seem quite so pig-headed for one direction or the other. But anyway, a very specific thing that you hear coming out of camps that don't like evolution is just a theory. And so these people are using this word theory in a way that is not the way scientists use it. They are using the word theory in such a way so that they can imply that evolution is not an established fact, that it's not actually knowledge worth having, or that evolution is not a known principle, that it's not actually knowledge that has been verified. Well, that's not what a theory is. A theory, well, let me see. Okay, right now, next slide. Okay, a theory, this is the definition I want you to have. A theory is a set of coherent ideas that guide analysis and help researchers to pose questions. So theories are not answers. Theories are ways to identify possible answers. They are ways to ask questions. They are ways to find the right questions. People often say that a theory of a crime, like in Sherlock Holmes, stories, is not a good way to talk about theories. I never got that. I think that a theory of a crime is a great way to talk about theory, because what did Sherlock Holmes do? Oh, he's a genius, right? Gosh. Well, what did he do? He collected evidence. He would find these weird little observations, like a pile of ash from somebody's cigarettes, and he would identify the brand of the cigarette from the pile of ash, because he once made a study of that. He knows about that kind of thing. And then what else does he do? Oh, he noticed a certain cadence in somebody's voice as they made a remark pertaining to the crime. Oh, and then there is the question of why was the murder victim's clothes turned inside out? And then why were all the doors unlocked, and why was the mirror turned around so it faced the wall? And so then what he would do is he would take all these strange observations and he would try to put them into a sort of overarching framework that would help him to ask the next question and to see which observations mattered and which did not, for the purposes of solving the crime, which was always what Sherlock Holmes was about. I think that's not a bad idea, not a bad way of thinking about science. They have to deal with all these different observations and experimental outcomes, and they have to put them together into a framework. And what the framework, this empirical framework, allows us to do is it allows us to guide our analysis and to pose more meaningful questions. And okay, I will butt heads with Richard Dawkins if you give me the chance. But this meme kind of says it all. No, it doesn't. It's just a joke. Gravity is a theory. You're not jumping out of buildings. If you get the urge to test the theory of gravity by jumping from things, by trying to fly, I just suggest you take off from the ground first. A little bit of advice from the comedian Bill Hicks. Oh, well, let's just get all these up. Okay, so again, a theory is a set of coherent ideas that guide analysis and help researchers to pose questions. And the best theories, conclusions, and evidence in science are, remember, based on empirical observations, engaged by a community of scientists and scholars, and they are assumed to be contingent or provisional. And the people who make these, I should add, should be open to challenge. So one part of the scientific method as you learned it in grade school that is actually worth talking about here is the hypothesis. A hypothesis is a way that scientists use to pose questions about the world. It's a statement. They make a statement about the world that could be true or could be false, and then they try to prove it false. And until they prove it false, the statement stands. This process is called falsification. It's where you try to find circumstances under which your statement, your hypothesis, could be false. So something to know here is that not all questions can be answered scientifically. Science cannot address everything under the sun. It can address almost anything that has to do with something you can knock on. But there are some things, some objects in our intellectual, symbolic world, in our world period, that cannot be addressed by science. So the hypothesis is really this gateway to figuring out if the question you have in mind is proper for science, is appropriate for scientific research. So if you want to test your hypothesis, test to see whether or not your hypothesis might be suitable for scientific research, I give you 3 questions to vet it with. Could other people answer or test this hypothesis if they had the same tools, training, and situation as you? Can my hypothesis be proven false? Right? If my statement that I'm making cannot ever be proven false, either because there's not going to be any evidence for it or because I don't intend for it to be proven false, then it's just not going to be helpful for science, right? These sorts of statements don't really reflect the reality of the world. You'll see what I mean over the next few slides. The third test I think you can apply to your hypothesis to see if it's appropriate for scientific research is, does this question deal with empirical phenomena? That is, does it deal with something you can observe? Now, something important to remember about empiricism and about observations is our observations don't have to be done just through our 5 senses. We have technology that can extend our senses. Radar, sonar, radio waves, heat imaging, all sorts of different things. We can look into the past, can't look into the future yet. Never, probably. I don't know. I won't say never, but there are limits. So just keep in mind, not all questions can be asked scientifically. So I'm going to show you a few hypotheses now, and what I want you to do is I want you to think about these hypotheses and whether or not they can be addressed scientifically. This is something we'll do on the discussion board on Blackboard. First hypothesis I want you to consider is men are stronger than women. Okay, so men are stronger than women. Is this a hypothesis that you could prove false? Is this something you could test with empirical observations? Think about it. How about we should protect gorillas? We should protect gorillas. Is that a statement that you can prove false? Is that a statement that you can support with empirical observations? How? He cheated on me. I'll let that one go. My cat thinks. That's a hard one. Think about it. I'm not suggesting that my cat thinks about boats. Just that my cat thinks. Can we falsify that? God is approximately 3,875,986,192,111 miles tall. Good or bad scientific hypothesis? I'll give you a clue. The question of whether or not God exists is really peripheral to whether or not this is a good hypothesis. Think about it. Triceratops had dark anterior coloring with a light belly. Regular orange mottling appeared on its back, and there were large spots on the frill and along the cheeks. The horns of males were pale with dark tips. Is that a good or bad scientific hypothesis? And I'll give you a clue. It does not have anything to do with how precise this description happens to be. Precise hypotheses are useful. But can this one be answered empirically? Can it be proven false? Brangelina's babies are more important than a room full of infant pandas. Look at all of those babies. Well, I have a parable for you. See, I'm getting you to think about hypotheses. I want you to understand that this is more than just a word game, right? Hypotheses are not about just playing games with words, making a statement that, that fits the criteria so that then you can do some science. Making a good hypothesis is about orienting yourself to the world in such a way that you can actually ask relevant questions about it. Making a good hypothesis is about recognizing the limits of what humans can and cannot know, and then working within those limits. So, sort of as another parable of science, I give you a short excerpt from the play Faustus by the German poet and playwright, I guess dramatist, Goethe. So Faustus here, seated on the left, he has summoned up the demon Mephistopheles on the right there, and he's made a dark pact with Mephistopheles. In exchange for selling his soul to Satan, Faustus is being provided with, I think it was 24 years of youth and health in his old age. So he basically, he gets a few more years to add on to his life and to be youthful and to live it in, quote, all voluptuousness. So, of course, Faust thinks he's got an angle on Mephistopheles and the devil. Faust thinks that if he's just given this extra time, he's going to be able to figure out the key to life, the key to immortality. And he thinks so by the end of this period that I've conned out of Lucifer, I'm going to have the key to immortality and I won't die anyway, so I won't have to go to hell and be tortured eternally by the devil. Ho ho. Well, these kinds of stories only work out one way, but I'm not here to warn people against doing daring and risky things, sometimes dancing with the devil a little bit. Rather, I think there's a section from Faustus that pertains really heavily to what we're doing when we're thinking about hypotheses. So let me just present it to you here. So still I seek the force, the reason governing life's flow, and not just its external show. The governing force, the reason, some things cannot be known. They are beyond your reach, even when shown. Why should that be so? They lie outside the boundaries that words can address, and man can only grasp those thoughts which language can express. What? So remember, I'm not saying anything in particular about language. That was what Goethe was talking about. Rather, I want to point out how language and these word games like hypotheses, and just the whole effort of trying to structure your thought into a way, into an orientation that will be fruitful for engaging with the material world that you can knock on. I want to stress that this is about recognizing our limits. So Faustus, he wants to work on a problem that's really just beyond his capacities. Mephistopheles thinks his capacities are limited by language. I think that it goes deeper. As somebody who's teaching you an evolutionary course, I think our capacities are shaped by our evolutionary history. At any rate, I want you to keep this thought on the bottom in mind. To formulate a hypothesis is to orient ourselves to the world, and on some levels to set the world up in such a way so that we can ask productive questions about it. So, is anthropology science? Well, I told you already, biological anthropology is science. Cultural anthropology is not, though. This chart, which I have gotten from the webcomic XKCD, is a joke. It's a joke. It's a joke. It's not a reflection on reality. This guy who does this comic, he's very savvy. A lot of people think he's sort of puritanical in his science, but they're misreading him. This here is a joke. But this does reflect a certain sense of hierarchy that people have when they think about the different kinds of knowledge out there in the world. I keep bringing up religion, for instance. There are so many folks, science fans out there, who just laugh off religion like it's just been thousands of years of some sort of joke. As if, now we've got science, we can just ditch all this other stuff. I would ask you to refer to the work of the atheist philosopher Alain de Botton, who suggests that even though he's an atheist, and he doesn't personally believe in God, there's still a lot of stuff that religion has done that's important, and it provides us with some very important capacities and techniques for engaging with the world. Now, I don't mean to defend religion in particular. It's just one kind of knowledge, faith knowledge, or exegetical knowledge, which is derived from the reading of texts. It's just one kind of knowledge that gets poo-pooed a lot because folks attribute sort of a greater purity or a more absolutivity to science. And then even within scientific research, some people will tend to see a hierarchy. So looking at the chart now, you could take sociologists or cultural anthropologists who study society and culture, and then you could just say, oh, well, really, sociology and cultural anthropology, well, what they're studying is just a byproduct of psychology. So if we understand psychology, we've already understood everything that sociology and cultural anthropology has to offer. Oh ho, but if you're a biologist, you could say, well, psychology, that's just the byproduct of the processes that we study. We're the guys who understand what nervous systems and bodies do and where your sense organs come in. Oh ho ho, the chemist could look at the biologist and say, oh, but those biologists, those guys, they're just studying the byproducts of the chemical processes that we study. So we've actually got a grasp on all this crap. Oh ho ho ho, says the physicist. The chemist is just studying the gross material, large-scale, macro-scale version of what we understand, the very fabric of the cosmos. Oh, ho, 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 says the mathematician, you physicists over there. You guys are still in the world? Look, I'm coming up with 1 + 1 = 2. You got something better than that? It's just a joke. Sociology is not contained within psychology, is not contained within biology, is not contained within chemistry, is not contained within physics, is not contained within math. The way knowledge actually works is a lot more like this slide. This is a really interesting slide. It's only marginally more accurate than the one I just showed you, but it's actually a lot more accurate than the one I just showed you, but it's also still just an incomplete representation of reality. What this actually represents, I'll tell you what the story with this is. Some researchers, what they did is they got their hands on every scholarly and scientific article they could get their hands on. And, they didn't even read the articles. What they did is they went to the bibliographies. If you're new to this college thing, bibliography, right? That's where you're going to cite all the articles that you read, all the articles where research was published that pertains to the research that you are talking about, to your own research. So these researchers, they went to the bibliographies of thousands and thousands of articles, and they checked who all these authors were reading. And what they found is that, for instance, somebody in music, somebody who's written some research in music. Well, what sort of articles are they citing? What sort of knowledge are they drawing into their own research? And so musical research has connections with, with religion, with classical studies, with architectural design, with philosophy. It also has connections with the natural sciences. Even plant biology there has a connection going over into music, or it looks. Let's pick another one. Applied physics. Wow. Yeah, applied physics is in the middle of a big mess. It's all the way at the kind of top right. Yeah, you look in that top right corner, you'll find it. Applied physics. Oh, here. In fact, I've got a pointer. I usually have a laser pointer, and I forget that I have an arrow pointer. So applied physics. Look at this. This big purple mess. It looks like a carnation almost, or baby's breath, I guess. Look at all the places that applied physicists are connected to. They're connected to these guys and these guys. It's kind of color-coded. So what are these pale peach ones? These pale peach ones seem to go up into manufacturing and maybe even like over here into the top parts of social science. So what this map shows is it shows you what kinds of knowledge is being drawn into disciplinary knowledge. So if I'm a geographer, what kinds of knowledge am I drawing upon? If I'm an anthropologist, what kinds of knowledge am I drawing upon? Anthropology, right here. Look at that. Ooh, we got connections all over the place. Yeah, look at this big mess. It's so hard to even tell what's going on here. Right? It's not a hierarchy, but rather it's lots of different kinds of knowledge that is continuously informing, that are continuously informing one another. So it's not like mathematics has the key to everything. Nope. Can we even find mathematics on here? Is there anything like that here? No, there wouldn't be, right? Such a dispersed field. But it's not like physics has the key to everything up here. Rather, it's just engaged with other things. Now look, physics has a bias. It seems to be engaged a lot with chemistry, a lot with engineering, and less with social science, less with natural science, less over here with medical science, less with the humanities. But it's still connected to these things. We still see little color codes here that suggest the social sciences and the humanities. Knowledge is really dispersed, and just there's no hierarchy, no greater purity in one kind of study than there is in another kind of study. We need to work together. Again, community, capital C, community of scientists and community of people who are scientists engaged with other scholars and with the public. A joke. I'll let you read this one. You can put the video on pause and read it. I'm going to go on through. If you are somebody in the humanities or the social sciences and you try to explain your research to an engineer or a physics person, this is often what happens. Moving on. I'm just teasing you guys if you're an engineer or a physicist. I'm just teasing. So, I'm going to show you a couple of URLs. I'm going to have you write these down and then go to YouTube. I probably will post something with a link to these two URLs. I'm getting these lectures done ahead of time, so this is not real time. I haven't actually met you, my students, yet. But I want to introduce the two characters in these videos I'm going to show you. One of them is Richard Dawkins, with his dashing smile here. Well, Richard Dawkins is a world-renowned geneticist. He's one of the most prominent public intellectuals in Britain and really all around the English-speaking world. His most important work has probably been The Selfish Gene, which was a book wherein he proposed to focus on genes as the basic unit of evolution. I think that's unnecessarily biased, but it's a good book. You should read it sometime. More recently, he's become famous in the rationalist circles and in libertarian circles especially, I've noted, for his work, The God Delusion. He is a major critic of religion, and well, he's riding that right to popularity, and well, he was popular before. He was always outspoken and kind of curmudgeon-y. He's made some important contributions to evolutionary research. We will discuss those later on in the quarter. For now, I'm offering him as a totem of positivism. A totem, a totem is it's an anthropological term. We stole the term from some I believe it's Northwest Pacific Indians. The way I use the term totem is I use it to indicate a person like Richard Dawkins here, who may be recognized as a genius. He's sort of a face or a figurehead that we can talk about, but really he represents something bigger. He represents a society of people, an association, a community of people doing research. That's sort of what a totem represents in anthropology. A totem, like there's an eagle totem represents the Eagle clan, right? That's a totem. So Richard Dawkins, he's a totem. All these scientists and other scholars I will talk about throughout this semester, they're all totems. Right? You already know I don't apply to the genius theory of science. These are totems. So Richard Dawkins, in the videos you watch, I want you to watch out for him as a positivist. Also, in these videos, you'll see Neil deGrasse Tyson, who right now he's most famous for being the new host of Cosmos, the miniseries, the reboot of the 1980s miniseries that used to star Carl Sagan. Neil deGrasse Tyson was the director of the Hayden Planetarium at the American Museum of Natural History, I believe, and maybe before this Cosmos thing happened, he was most famous as the guy who said Pluto was not a planet. Whatever, planet, potato, it's still a big thing that orbits around the sun. I don't understand why the guy got so much sad hate mail from like fourth graders, but I don't know. I want you to think of him as a relativist. Now, both of these gentlemen are going to be relativists to some degree and positivists to some degree. But in the video, the URL I'll bring up in a minute here, I want you to just think of Neil deGrasse Tyson as a totem of relativism. He's an astrophysicist, and like most astrophysicists, he starts from this theory of relativity from Albert Einstein, and figures that anywhere you are in the universe, whatever your observations are there, they are going to be accurate only for that position in the universe. A third person who is not going to be in these videos, he would never be invited to a talk like The Poetry of Science, which is what the video is called, is Richard Lewontin. Richard Lewontin is a biologist. He was a Harvard biologist. I think he's probably emeritus now. I'm pretty sure he's still alive. His angle is that, well, science is a social product. Science is a product of communities. And the science that gets done is the science that gets funded, is the science that is popular, and is the science that is deemed useful by powerful parties. So there's a basic consequence of this, which is to say that scientific knowledge, whether it's relative or positive, is shaped by power in the world. Do you know who funds most of the scientific research in the world? Governments and militaries. No joke. Check it out. And so that has an effect on the kind of knowledge that we produce with science. I'm not saying be suspicious of science. Geez, no, I'm a great science fan. For some reason, some of my students think I am anti-science, and that I'm an apologist for religion. Man, I get these cranky types all the time. Neither of those are true. I think there's things to value in religion, and I love science. But I want you to keep Richard Lewontin's lesson in mind, that science and scientific knowledge is not produced in a vacuum. It's produced by real people in a real world who are affected by power. Real people who have careers to make, who have to get a paycheck, who have loans to pay back. Yeah, try going to grad school for science. Well, it's not as bad as going to grad school for the humanities or the social sciences. You got to get your loans paid back. Anyway, Richard Lewontin's quote, Consciousness of what it is to do real science has been formed in a world dominated by manipulators of nature. He's saying that the sort of science superheroes that we've had in the 20th century, these geniuses, these totems, these mad scientists, the ones that people have paid the most attention to, the ones that people have paid the most money to, the ones who have gotten the most public acclaim and appeal, are people who have been making claims to be able to manipulate nature. Now, it's true, science does allow us to manipulate nature, and I will teach you later on in this course all about the many ways that humans have of manipulating the world around them. But I also want you to think about this. In a world where our superheroes are manipulators of nature, what is it that people think we are doing when we do science? A lot of science gets done now with the goal in mind of mastering nature, dominating the world. A lot of science that we do gets done now with this notion that we are in a position of power vis-a-vis the rest of the world, that we are, in some sense, transcended the world. That, well, we've got science. Great. Now, we don't know everything yet, but we've got science. It's the last tool we'll ever need. We just need to fill in the details. I do not think science is the last tool. I think we'll come up with some other tools later on. Some crazy tools. Man, I love science fiction. Thinking about the future, something we can never know. Anyway, just keep that stuff in mind as you watch Neil deGrasse Tyson and Richard Dawkins take questions from the audience. So the first URL here is this one. Just this. It's about an hour and a half long. If you are a real science fan, you will love watching this. It's good stuff. They talk about so many interesting topics. But I want you to watch it, and I want you to watch Dawkins and Tyson for their positions about knowledge. How do they feel about scientific knowledge? How do they feel about the authority that science has? And how do they feel about the truth? If you don't want to watch the whole video, I suggest starting at 1 hour, 2 minutes, and 46 seconds, where Tyson and Dawkins are responding to a philosopher. My personal take on this is that they just dismiss the philosopher in the audience far too summarily, and they both express, I think, problematic approaches to philosophy. A couple of scientists saying, well, if you're not doing science, what are you doing? And saying, why, Tyson in particular seems to lament that so much intellectual energy is being put into philosophy instead of science. Maybe I'm misreading him, because he's a really reasonable guy in other aspects. Anyway, after you get done watching that video, there's a second video here. It's called Tyson versus Dawkins, and it's only about 2 minutes long, or 2.5 minutes. You must watch the whole thing. It has some cursing in it. I'm warning you. No, they're not cursing at each other. But this little 2.5 minute video, I think, will be perhaps the best summary of the consequences of having a positivistic point of view. You may have realized by now, as a cultural anthropologist, I'm a bit of a relativist. If you're interested in that, or finding out more about why I hold a particular point of view, you're always free to write me or ask me in the discussion forum. And as a relativist, I want you to watch this 2.5 minute video, and I want you to think about the consequences of being a positivist, of approaching the truth in the way that Richard Dawkins does. I'm sure some of you will have different ideas about all this, and maybe we can have them in discussion. Well, that's it for this lecture. I'm getting a little hoarse, and so I'm going to get some water, stretch my legs, and I hope you do the same thing. I'll see you on the discussion board. Adios.